All right. This is a video about. My name is Mark Dittmer from American Indian Public Charter High School, and this is a video about graphing. So objective is graph the cosine function of the form. Now I'm going to write it in two ways. Y equals cosine x is the parent function, and y equals. So variations on it can be made using a multiplier in front, and it's a times cosine bx. So a multiplier in front of the whole thing, and then a multiplier in front of just in front of the x, the thing that's finding the cosine of, right? So in our last video we were talking about y equals sine x and y equals a sine bx, and we saw that looked like this, where the amplitude was 1 and the period was, and just to get a hold on the period is how long the whole function takes. You might say, like, well, why isn't this the period, Mr. Dittmer, from here to here? Because the period has to include everything that happens to it, the hill and the valley. So from the beginning to the end of hill valley, you get 0 and to 2 pi. So the period is 2 pi. So for y equals sine x, amplitude is 0, and period is 2 pi. But what about y equals a sine bx? Well, it depends on what a and b are. If they're both 1, we're doing the same thing. But if what is O? An accident, is what that is. And we talked about how A changes the amplitude, not the midline, not the period, but the amplitude. But what does B do? Well, when B gets bigger, the period gets smaller. And there's an exact correlation with how much. So like if B doubles, the period is 1/2 of what it was before. So, and if the B shrinks by 1/2, then the period is now double what it was before. So the way we express that is we say for a sine bx, the amplitude is, well, it's the absolute value of A, and the period is 2 pi divided, period is 2 pi divided by B. That's the period. And so if B gets bigger, the period gets smaller. If B gets smaller, the period gets bigger. Notice that small period looks like this, and large period looks like this. And what we call that in terms of sine waves are called, they're waves, and they're like they're good for modeling radio waves. And when we have waves with low periods, we say they're high frequency. So the lower the period, the higher the frequency, and the higher the period, the higher the period, larger the period, the lower the frequency. So I think that may correspond. Now I'm just making stuff up, but I think that high frequency might be like higher pitch, like high. Like if you talk in a falsetto voice, a really high voice, you're using high frequency, and if you talk a really low voice, you're using low frequency. But the period is the opposite of the frequency. So that's all sine, but it's worth reviewing here because I'll make a new, because the cosine graph is very similar. So again, I'm going to go back to this Math is Fun interactive unit circle to explain it. So when we're talking about sine, we focused on red. Now when we talk about cosine, we're going to focus on blue. So now we'll try to ignore red and focus on blue. Now again, cosine is derived from a triangle placed on this axis, and the adjacent side, the side adjacent to that angle is the x side, and it starts out almost as big as the hypotenuse. So therefore, the cosine starts out at 1, and then slowly the cosine goes to 0. We're looking at that blue line, and then becomes negative all the way to negative. It tops out at -1. Then blue line comes back to 0, and then blue line goes to +1. So think about, what do you notice and what do you wonder? And think about, first, how is this different from the sine wave? How is the blue line different from the red line? And how is it the same as the sine wave? And if hopefully maybe you paused that and came up with some ideas. One of the similarities I hope you came up with was that it has the same amplitude, right? 1 is the max, 1 is the minimum, so 1 is the amplitude. The other thing I hope you came up with is that the midline is still the same. Still y equals 0. Which leads to one obvious question: is the period still the same? And the answer is, yeah, it is. Because this doesn't repeat itself until it's gone a full 360 around. And in that 360, it does go through its entire cycle, right? Now, it crosses 0 twice during that cycle, but part of that is a valley, and part of it is a peak, which is just the peak is split up on this one into the beginning half of the peak and the end half of the peak. But overall, you still have a period of 360 degrees, or 2 pi radians. So let's see what that looks like if we graph it. Say y equals cosine x. And you can see it sort of going, on the same, you might guess that it's shaped the exact same as the sine wave, and you'd be right. It is the exact same. The way it goes from 0 to 1, back to 0 to -1, just like the sine wave does. From 0 to 1 to 0 to -1. And it takes just the same distance to do it, and if we don't use the word slope, that's for lines, but it has the same curve, the same shape. So we've got the same shape, same amplitude, same period, same midline. And some of the descriptions we used to, some way we can summarize this is we can say the amplitude for both these functions is, now I said it was 1 for y equals cosine x, but if I call this y equals a cosine x now, and I move a, the amplitude will change, right? Just like it did with the sine function. I can make them both change. And the way the b affects it, we say, well, I wrote this on the chart for you, but yeah, period is 2 pi over b, so that's true of the cosine function as well. Same effect. When you change b, the effect is the same. B gets big, period gets small. B gets small, the period gets big. And yeah, I mean, not a whole lot else to say about the cosine function. So I'm not going to try to make this drag on. I do want to show you one word problem though, because the waviness of these functions when you graph them um, makes them useful to model. There's a lot of things in nature. Sound waves are just one of the things in nature that look like this. So you'll get problems where they say, like, a sound wave is modeled by the equation y equals 4 cosine bx. And you'll use this graph and you'll be talking about a sound wave. The problem that I've copied down talks about a pendulum. So this is the motion of a certain pendulum can be modeled by this function. And well, obviously, and I've got a drawing of the pendulum over here. Obviously, this doesn't look exactly like a sine wave. But what if I'm just measuring horizontal displacement? So I'm just measuring what is its x, what is the x value of this thing? I'm ignoring the vertical thing and I'm just saying, the x value goes like this. But now if I just take the x value, and since I'm modeling that over time, I'm going to take the x value and put it on my y-axis. So this left, right, on my graph is going to become up, down, up, down, up, down. So I'm modeling the left, right with an up, down graph, right? Kind of a weird idea, but we can graph what we want to graph. So if I want to graph horizontal displacement, I can do that over time on the x-axis. So I'm going to model it this way. So they gave me the equation. I know that I'm going to use this because I just learned it. I got lazy and didn't complete my x. So then I know d is going to be my y. So my horizontal displacement I'm going to model on the y. Time is going to be my x. And so what is, how far does the pendulum travel from its original position? Well, when it asks me that, is it asking me for period, midline, or amplitude? Think about it. How far does this travel from its original position? What's this distance? Correct answer is amplitude. That's the amplitude from midline to the maximum. So what's this? 4. So my answer is right there. It's 4 inches. How far it travels from its original position is 4 inches. The next thing it says is to graph this, so I can go ahead and try to graph it on Desmos 4 cosine 8 pi over t. The only reason I wrote pi like this is because of the software I was using here. I couldn't write pi the normal way. 4 cosine 8 pi t, so I'm just going to write it y equals 4 cosine 8 pi x. Oh. So very high frequency, right? Very high frequency. I'm going to zoom in and see if I can catch. So it looks like from 4, way up at 4, it went straight down here and then back up here. And here, I guess if we go to 4, kind of move. There we go. There I can catch a, oh, it's 0.25. So the period must be 0.25. How would I get 0.25 from why 0.25? Well, remember period is 2 pi over b. B is, in this case, 8 pi. So 2 pi over 8 pi. The pi's cancel out. 2 over 8, 0.25. That makes sense. So, wow, what a short period, right? 0.25. Every 0.25 seconds, the thing does a full cycle, goes boom, boom, boom. But the problem didn't ask for the period. The problem only asked for the amplitude. Remember, b is not the period. That's a common mistake with all this, with sine and cosine functions. So something to remember: b is not the period. It's the thing in the equation. 2 pi over b is the equation. Excuse me. 2 pi over b is the period. So looking back at this problem, well, I can't look back at this problem because I just erased it. But when in our problem, it was. They gave us y equals 4 cosine 8 pi x. So b is 8 pi. So in that case, b equals 8 pi. So then the period is 2 pi divided by 8 pi, or 0.25. And that's what we saw on the graph. The period, they did one full cycle, 0.25. Okay, hope that makes sense. Thanks for watching. See you in class.